All right, let's dive into something that's, well, pretty much running the world behind the scenes, machine learning. It's the secret sauce in so much of the tech we use every single day, and today we're going to break down exactly what it is and how it all works.
Seriously, have you ever stopped to think about it? How does Netflix just know what movie you want to watch next? Or how does your phone magically pull up every single picture of your dog, even the blurry ones? It feels like magic, right? But it's not. It's machine learning. At its heart, it's all about teaching computers to get really good at spotting patterns and making smart guesses based on data.
Okay, so let's get into the big idea. What is machine learning really? So the official definition is that it's a part of AI where systems can learn from data, find patterns, and make decisions all on their own. But here's a simpler way to think about it. For decades, we told computers exactly what to do, step by step. If this happens, do that. Machine learning completely flips the script. Instead of feeding it rules, we feed it a ton of data, and it figures out the rules for itself. It really is like the old saying. Instead of giving a computer a fish, we're teaching it how to fish.
And what makes this so powerful? Well, a few key things. It's totally data-driven, which means the more data it sees, the smarter it gets. It's constantly improving. Its main superpower is pattern recognition, and that superpower is used everywhere. We're talking about computer vision that helps a car see a person crossing the street, natural language processing so you can talk to your devices, and even trying to forecast where the stock market is headed. It's a huge deal.
All right, so we know what it is, but how do machines actually learn? Turns out there are a few different flavors. Let's start with the first one, learning with a teacher. This is what we call supervised learning. And honestly, the best way to picture it is like studying for a test with flashcards. You've got the question on one side and the correct answer right there on the back.
The magic ingredient here is something called labeled data. You're literally giving the computer a giant answer key to study from. Imagine you want to teach it to recognize cats. You'd feed it thousands, maybe millions of pictures, and every single one is tagged or labeled with cat. After a while, it starts to see the patterns, the pointy ears, the whiskers, the catness of it all. So when you show it a brand new picture it's never seen before, it can look at it and go, yep, based on everything I've learned, that's a cat.
So the end game for supervised learning is all about prediction. We use all those examples with the answers we already know to train our model. Then we test it. We give it new problems without the answers and see if it gets them right. And just like a teacher, we grade its performance using things like accuracy and precision. We're literally checking to see if it did its homework and learned the lesson. And believe me, you see this stuff everywhere. You know that spam filter in your email that just thankfully works? That's a supervised learning model that's been trained on millions of emails labeled as spam or not spam. Or when you see a website that estimates a house's price, same idea. It's even used in medicine to help diagnose diseases. All of it comes back to learning from examples that already have the right answers.
So how do you actually build one of these things? Well, it's a pretty clear workflow. First, you got to get all that labeled data, and trust me, you have to clean it up. Then you split it up and start the training process. This is where the learning happens. After that, you evaluate it, you test it to see how well it did. If it's not quite good enough, you go back, you fine-tune some things, and you train it again. You just keep rinsing and repeating until it's ready to be deployed out into the wild.
Okay, supervised learning is amazing, for sure, but it has one pretty big weakness. It needs that perfect answer key. It needs all that labeled data. So, what do you do when you don't have one? What happens when you're just handed a giant pile of data with no labels, no answers at all?
Well, that's where our next type comes in, finding hidden patterns with unsupervised learning. I love this analogy. Picture yourself as a detective. Someone drops a huge box of case files on your desk, but there are no labels, no notes, no clues. Your job is just to find the connections, to group things together and see what hidden patterns pop out.
So if labeled data was the key for supervised learning, then unlabeled data is the name of the game here. We aren't telling the machine what to look for at all. We just dump a whole lot of data on it and basically ask, hey, find something interesting in here. See if you can sort this mess out on your own. It is pure discovery.
In this scenario, the algorithm is like a data explorer venturing into unknown territory. The goal isn't to predict a specific answer, because there are no answers to predict. The goal is to find the hidden structure that's already in the data. It starts automatically grouping things into logical clusters, and sometimes it finds connections that a human would have never, ever noticed.
And oh man, businesses love this stuff. An online store might use it to group shoppers into different buckets, like bargain hunters or high-end buyers, without knowing those groups existed beforehand. You've probably heard of market basket analysis, that classic example of finding that people who buy diapers often buy beer. That's unsupervised learning. Even banks use it for anomaly detection, finding that one fraudulent transaction that just doesn't look like all the others.
Okay, so machines can learn when we give them an answer key, and they can learn by finding patterns on their own. But what about learning from just doing things? You know, from pure trial and error, from experience. That brings us to our third and maybe most exciting type of machine learning.
We're talking about reinforcement learning, and the absolute best way to understand this is to think about how you'd train a pet. When your dog sits, you give it a treat. That's a positive reward. If it chews on the furniture, maybe there's a negative consequence. Over time, it figures out which actions get it the most treats.
So let's get just a little technical for a second. In reinforcement learning, we have an agent. That's our learner, our AI. This agent exists in an environment, which could be a video game, a simulation of a city, whatever. The agent takes an action. The environment then gives back two things, a new state and a reward or a penalty. And the agent has one single goal in life: learn a policy or a strategy to take actions that get it the most possible rewards over the long run. What you see here is that core feedback loop. The agent looks at the situation, it takes an action, and it gets a reward or a penalty back. That action has now changed the situation, so the agent looks again, takes another action, gets another reward, and this just keeps going over and over. It's a constant cycle of doing, getting feedback, and updating its strategy. It's literally learning by doing. Now, this is where it gets really interesting. The agent is always facing a tough choice, what we call the exploration versus exploitation dilemma. Should it exploit what it already knows works and just keep getting that guaranteed reward? Or should it explore by trying something totally new and random that might lead to a way bigger reward or might lead to nothing? Finding that perfect balance between sticking with what works and trying new things is the secret to mastering the environment. And the places you see this, it's mind-blowing stuff. This is the exact technology that powered DeepMind's AlphaGo, the AI that beat the world's greatest human Go player at a game we thought was too complex for computers. It's a key part of how autonomous vehicles learn to drive, how industrial robots optimize their tasks on the fly, and even how complex financial trading algorithms work. It's really on the cutting edge.
So there you have it, the three big ways machines learn: learning with a teacher, learning by finding patterns, and learning from experience. Let's put them all side by side so we can really see how they stack up.
When you look at how they learn, it all comes down to their main goal. Supervised learning, it's all about making predictions. It needs that labeled data with the answers. Unsupervised learning, that's about discovery. It's sifting through unlabeled data to find hidden structures. And reinforcement learning, that's all about taking smart actions in an environment to get a reward. Totally different goals, totally different kinds of data.
And because their goals are so different, what they're used for is also worlds apart. Supervised gives us those everyday workhorses like spam filters and price predictors. Unsupervised is the secret weapon for businesses doing things like customer segmentation. And reinforcement learning, well, that's powering the future with things like self-driving cars and game-beating AIs. Each has its own toolbox of algorithms designed for its specific job.
So to wrap it all up, we've seen the three fundamental ways machines learn. They can predict, they can discover, and they can act. And that leaves us with, well, a pretty huge question, doesn't it? Now that we understand how these powerful systems learn, we really have to think hard about what we want to teach them next. The possibilities are pretty much endless.